All right, welcome everyone. Today, we're going to tackle a huge concept in linear algebra, linear independence. Now, I know it sounds super technical, but trust me, at its core, it's all about a really simple question. How much information do you actually need? Let's jump in.
So, let's just imagine for a second. You're on a street corner and someone asks you for directions. It's a simple, everyday thing, right? But it's the perfect setup for everything we're about to unpack.
Okay, so you tell them something simple, like go 3 miles north and 4 miles east. Boom, that's it. You've given them two key pieces of information, a north direction and an east direction. They're distinct, they point in different ways, and together they get you exactly where you need to go. It's a perfect, clean, efficient set of instructions.
But then, what happens if your buddy chimes in with this extra tidbit? Oh, and by the way, it's 5 miles northeast. Now, he's not wrong, but is that information necessary? Does it actually add anything new, or is it just extra? This is the exact question that linear independence asks.
Okay, so let's dig into that northeast direction because it feels a little redundant, right? Intuitively, we know we don't need it. And in linear algebra, we have a precise way of talking about why.
See, here's the thing. That northeast direction, it's not some new magical piece of information. You can already build it just by going north and then east. Since we can construct it from the other two, it isn't adding anything unique to the mix. It's totally redundant. And you know, this whole idea of essential versus redundant information is so important that, of course, mathematicians have some fancy names for it. So let's get the terminology straight.
All right, here's the breakdown. When you have a set of directions and at least one of them is redundant, like our northeast example, we call that set linearly dependent. On the other hand, if every single piece of information is crucial, like our original north and east directions where you can't get rid of either one, well, that's what we call linearly independent. So it really just boils down to one question. Is every direction you have absolutely essential?
Okay, brace yourselves. Here comes the official math definition. But seriously, don't let it scare you off. All this equation is really asking is this. Is there any way to combine these vectors, to walk along them for some amount, that gets you right back where you started without just sitting still? If the only possible answer is the boring one, taking 0 steps in every direction, then congratulations, your vectors are independent. It means they're all pulling in their own unique way.
You know what? Let's boil it down even more. This quote right here really hits the nail on the head. Basically, if you can cook up one of your vectors using a recipe of the others, then the whole set is dependent. That's it. That's probably the most intuitive way to think about this whole thing.
All right, that's enough equations for now. Honestly, the best way to get a real gut feeling for this stuff is to actually see it. So let's look at some geometric examples.
Just think of vectors as arrows on a tabletop. Simple enough, right? If you have two arrows pointing in different directions, great, they're independent. But what if they're parallel? Well, then one is just a stretched out or shrunk down version of the other. They're on the same line. That makes them dependent. And here's where it gets really cool. Throw a third vector onto that same 2D table. Any third vector. I guarantee you this set is now dependent. Always. You're trying to describe a flat world with 3 directions. One of them has to be extra. Oh, and one more thing. The 0 vector. The instruction to go nowhere? Yeah, that guy always makes a set dependent. Total freeloader.
Let's put some actual numbers to this. So look at that first set. The vectors 1, 1 and -3, 2. They're independent. Why? Because you can't just scale one up or down to get the other one. They point in truly different directions. But look what happens when we throw in that third vector, 2, 4. Now the whole game changes. It turns out you can actually cook up 2, 4 by taking a specific combination of the first two. And because one of them is now just a mix of the others, the whole set is, you guessed it, linearly dependent.
Okay, so who cares, right? Why does any of this matter? Why are we so obsessed with whether vectors are independent or not? Well, it's because this idea, it helps us find the most basic fundamental building blocks of any space.
And that leads us to this really elegant and powerful idea called a basis. Think of a basis as the perfect, most efficient set of directions you can possibly have. It has 0 redundancy, every vector is independent, and you can use them to get literally anywhere in that space. It's like the skeleton key for an entire dimension.
And the most famous, most intuitive examples are what we call the natural basis vectors. For a flat 2D plane, it's just take 1 step east, which is 1, 0, and take 1 step north, which is 0, 1. Sound familiar? And for 3D space, you just add that third up direction, the z-axis.
These are the absolute bare-bones essentials for our standard coordinate systems.
And that number right there, 2, that is so important. For 2D space, like a sheet of paper, you need exactly 2. 2 and only 2 linearly independent vectors to build your basis. That's not a coincidence. The number of vectors in your basis is the dimension of your space. They're one and the same.
Okay, so all of this builds up to a really powerful, super practical rule of thumb. It's something you can use anytime you're looking at a bunch of vectors.
And here it is, the big takeaway. If you're working in an n-dimensional space, let's say 3D for example, and someone hands you more than n vectors, so say 4 vectors in 3D space, you know, without even touching a calculator, that the set has to be linearly dependent. It's just too crowded. You've got too many directions for the space you're in. One of them is absolutely 100% guaranteed to be a combination of the others.
And look, this isn't just about geometry and arrows on a page. This idea of finding a basis, of finding those essential independent building blocks, is everywhere. It's how we compress digital photos by figuring out the most important pieces of visual information. It's how we analyze sound waves by breaking them down into their core frequencies. It's used in economics, in data science, you name it. So that leaves us with a bigger question to think about. In all the complex systems around us, what are the essential building blocks and how can we find them hiding in plain sight?